Section 7.3, we're going to be looking at finding volumes using what we call the shell technique. And what we're going to do is we're going to create cylindrical shells around our axis of revolution. Now, this comes really handy when the washer technique is going to be miserable. So to give you a miserable example, if we consider the following region bounded by y equals negative x squared plus 6x minus 5, that's our blue curve, and y equals 0, that's our x-axis. Suppose we want to revolve this about the y-axis. Well, if you were to do the washer technique, here's going to be in green my reference rectangle. Now, right now, hopefully you can see we got a little bit of a strange situation that's going to occur. My capital R of x, going from the axis of rotation all the way to the longest part of my rectangle, is the blue curve. And then my little r of x, that's the shortest distance, it's the same function. So that's going to be a little bit different here because they're going to have that function squared minus the function squared. Everything's going to cancel out. It's not going to work very well. All right, so that's going to be very difficult to do. All right, so here's what we're going to do. We're going to look at our representative rectangle being parallel to this axis of rotation, which is the y-axis. If we do that, we get a shell. So let me give you a picture of that. Here it is. There's my shell going around. There's that rectangle that was parallel to my axis. So it makes, if you will, one of those open pasta noodles, if you will. All right, hence the name shell. So here, my radius is going to be the x. The height of my shell will be the f of x function. And what we're going to do is we're going to cut this shell and unroll it to make this giant rectangular shape. And now the length of this rectangle is 2 pi x, which should look familiar to you. That is your circumference of our circle, 2 pi r. So you can mix this up. It doesn't matter. Some people call this f of x, but we're going to change it to h of x because in order to do the shell technique, you need to multiply the radius, which we'll call r of x, times the height, h of x, and then we'll multiply that to our change in x. So here's my length times my height times the thickness will give me the volume of that rectangular box right there. All right. Okay, so as we create our formula, 2 pi r, that's our length, times our height, which is going to be that h of x or f of x, times your thickness. So if we use our limit notation, here's our approximation of all these rectangles, or excuse me, not rectangles, they turn into little boxes, if you will. And if the number of our boxes approach infinity, when we find our limit, then that turns it into an integral. So if you have a vertical axis of revolution, all right, we want to be parallel to that, like we did in our example. So we will have 2 pi, we'll factor out the 2 pi to the front, integrate it from a to b, and we'll multiply rx times the h of x and multiply it by dx, integrating with respect to x. If you have a horizontal axis of revolution, then all my x's now become y's. All right, and then we integrate from c to d, whatever on our y-axis. All right, so let's go back to that ugly example that we said the washer technique wouldn't work. Here we are, right here. And the highest point of this parabola is 3, 4. And here's an x-intercept of 1, here's a 5, so this is where I'm going to integrate from 1 to 5, lower bound, upper bound. So Here's my xy. This rectangle is going to be rotated around the y-axis, so my radius, bing, is just going to be the x coordinate that I'm working with. When x is 1, that's my radius for my shell right here. And then my shell, they get taller in height, and my radius goes all the way up from 1 to 5. The height of my rectangle, that's my blue function. The negative x squared plus 6x minus 5. That's my height. So I have everything I need. I have my change in x, I have my radius, I have my height. So let's substitute it in. 2 pi times the integral from 1 to 5. Radius was x. H of x was the negative x squared plus 6x minus 5. Thickness is dx. We'll distribute the x, and then we integrate it. So negative x cubed plus 6x squared minus 5x. Integrate that. We're going to get negative x to the 4th over 4 plus 6x cubed over 3 minus 5x squared over 2. The 3 and the 6 reduces to a 2. So here, we don't have a 0, we have a 1, so we're going to have to keep track of our substitutions. So if I put in my 5, again, you can put this in as negative 5 to the 4th power over 4, plus 2 times 5 to the 3rd, minus 5 times 5 squared over 2, minus my next set of parentheses, putting in the 1s. Well, if you put 1 in for all these x's, negative 1/4 plus 2 minus 5/2. Either way, that's a lot of fraction work. I'm going to my calculator. My calculator tells me it comes out to be 32 times my 2 pi. We're at 64 pi units cubed. Okay? Now, again, just to recap all your techniques, you have your disk. Our formula is pi times r squared times delta x. Remember that your rectangle has to be perpendicular to your axis of revolution, and there is my integral formula. All right, capital R of x, or just capital R squared dx. Washer technique, we're not touching our axis of revolution. We usually have 2 curves here. All right, remember it's capital R squared minus little r squared, then times the pi. We're still perpendicular to the axis of revolution. There's my integral. And again, we can switch these all out, if you will, if we had to have them with a vertical axis of revolution. We're just revolving them all around the x. So here, the shell technique, you have to be parallel to your axis of revolution. So this is going to be a change in y, my delta y here. So 2 pi times the r function times the h function, radius and height, and then your thickness is delta y. Again, always parallel. That's the symbol for parallel. So v equals 2 pi times from c to d, the integral from c to d, r times h times dy.